Okay, so just a quick review with what we did on Wednesday. So we started talking about Newton form of interpolation. So what is the Newton form? So because Lagrange form, every time you have a new point, then you have to compute the whole Lagrangian polynomials again. So we start to introduce Newton form. So Newton form assume that the interpolation data yj come from a function, okay? So some function f, and then we start, like introduce the polynomials pm. So pm, it just interpolate up to degree m of the first m plus 1 points, yeah? So when m equals 0, then it's just a constant, okay? What is just the value at the first point of the function? And when m equals 1, then p1 is just a line, yeah? So the pictures look like this. So I draw some pictures yesterday on Wednesday. So in general, you can define the Newton form of the interpolation polynomial of degree n in this form, yeah? And now the coefficient a1 up to an are called the divided difference of the function, okay? And the divided difference with respect to the point xj, and you denote it by f, then the collection of points within the square brackets. And now, yesterday on Wednesday, we discussed how to get the coefficient, right? So the coefficient for 1 point is just the value of the function itself, okay? And then for 2 points, then the coefficient is just the slope of the line that go through 2 points. Go to 2 data points, yeah? And now we discuss how we get the divided difference over 3 points. So the idea is, you consider the you consider the following picture. So can we see it? Or where is the lamp here? Yeah. Is it better? Maybe it should be. Anyway, so the pictures look like this. Okay, so you consider only 3 points, x1, x2, and x3, yeah? So P2, P2 is the parabola that goes through 3 points, okay? And the parabola P2 can be constructed from P1. So P1 is the line that connects fx1 and fx2, okay? So you construct P2 from P1 by adding the next term. So this one is like you construct P2 from the left, yeah? But then you can construct P2 from the right. You can start from Q1, yeah? You can start from Q1. So the line that connect fx3 and fx2. And then you construct P2, yeah? And then that process is summarized into 4 equations, 1, 2, 3, and 4. And you can see that, you see, P1 is just a line that goes through x1 and x2. Okay? And Q1 is just a line that goes through X2 and X3. And now P2 is constructed from P1 plus this term. Yeah. So this is from the left, and from the right, P2 can be constructed from Q1 with this term, right? And now you just, compare 1, 2, 3, 4. So just subtract P1, Q1 and P1, Q1, yeah? And then P1, Q1 from two ways, either from 1, 3 or from 2 and 4, okay? And on the left, they are the same. So it means that the right, they have to be the same. And on the right, you just work out the details, but we just summarize that on the right, you just pay attention to the coefficient for x only. And because they are the same polynomial, so the coefficient for x has to be the same, right? So we ignore the remaining terms. We just say that, okay, the polynomials are the same, so the constant for x has to be the same, so therefore this coefficient has to be equal to this coefficient. And then you get the formula, okay? So now the formula looks complicated. However, in practice, it's very easy to compute. So now, so this works for any xj, xj plus 1, xj plus 2, okay? So we don't have to worry that x1, x2, x3, but it could be any 3 points. And so now, you can use the same method to prove that the divided difference for 4 points can be computed by this formula. So divided difference in 3 points, take the difference, and x4 minus x1, and so on. Using induction, you can have a divided difference for k plus 1 point. Okay? So now, when you start to put things in the table, and it's arranged like this. So this one is the divided difference for 1 point. Yeah? And you see, like you just take fx2 minus fx1, then you get this divided difference for 2 points. Okay? And so on. We have this divided difference for 2 points. And for this 3 points divided difference, then you just take the difference of those two guys and take the quotient between this minus this divided by x1 minus x3. Okay? And the last one, you just take the difference of those two terms minus x1 over x1 minus x4. Okay, so now let me do one example. Yeah, so you see, look at this. I do it by hand now, and you can compare with the one in the lecture slide. So suppose, remember, we have the x and the y here. So the x and the y is 0, 1, 2, 3. Yeah. And the y is just 2, 0, minus 3, and 5. Yeah. So now I compute this number. So this number will be 2 minus 0 divided by 0 minus 1. Yeah, what is just minus 2? Okay, so you got minus 2 here. Okay, and then for this number you just take 0 minus 3, so it becomes plus 3, and 1 minus 2, so it becomes minus 3. Yeah. So you got minus 3 here for the second one. And for this one, you got minus 3, minus 5, 2, minus 3, so 8. Yeah, so that's why you got number 8 here. Yeah, got it? And for this one, for this term, then you have minus 2, minus 3, so minus 3 becomes plus 3, divided. Now you have to take this 0 minus 2. Okay? So it gives you so minus 1/2, yeah, so you have minus 1/2, so that is here, okay, and so on. So now you just do the same. So this one is like you got minus 3 minus 8 and 1 minus 3, so it gives you 11/2, yeah, so and so on. So then the next one will be, you know, minus 1/2 minus 11/2 divided by 0 minus 3, okay, and it gives you so this one is like minus 6, so minus 6 over minus 2, so it's 2, yeah, so it gives you exactly this table. So you see that even the formula looks complicated, but in practice when you put down in a table, that is very easy to compute, okay. And now how do you rid off the polynomials? So the polynomials is, look at this coefficient. So the coefficient can be rid off from the red numbers. So 2 here, then 2 here, yeah, minus 2 here, minus 1/2 here, 2 here, then 2 here, okay. And so see now the first term is a constant, and now this one is x minus 0, right? And this one x minus 0, x minus 1, and then x minus 0, x minus 1, x minus 2. Okay, so this is identical to the general formula, you know, but you stop. So this is the general formula. Yeah, you stop when you up to the last point. Yeah, and actually the process can be automatic. So if you go to Moodle, there's a MATLAB function that allow you to compute this divided difference table very quickly. Okay, so now if I go to, okay, so this one is the function that compute the divided difference table. So you can go to Moodle and you can download these files. Okay, so this one it takes in the x data, so it's a vector, and the y data is another vector. And the table of divided difference is stored in the matrix T, in the n by n plus 1 matrix T. Okay, and the formula is given here, so you have to manage the index. Yeah, so you have to look at the index, how we computed the divided difference. But then, so suppose I run this. So suppose I run this program, yeah. So suppose my x data to be essentially this 1, 0, 1, 2, 3, okay, and y data to be 2, 0, minus 3, 5, okay. Then I just use DD to compute the divided difference. Okay, so now where are the coefficients? Where are the coefficients in the table, in the matrix? So do you see where is the coefficient? The first row, yeah? The first row is the coefficient. Remember in the, so you have 2 minus 1/2 and 2. So remember in the slide, so you have 2 minus 1/2 and 2. Because you see, like, it's not easy to represent a triangular table like this in MATLAB. So I just, you know, like move it up. So make this one the first row. It looks easier, at least in terms of programming. Yeah, but this is how you compute it by paper. It looks easier for you on paper, But for MATLAB, it's not easy. Yeah, so MATLAB, we have to make this one is like the upper triangular matrix. Yeah, then MATLAB can compute it easily. So, yeah, so this one is the output. So I just ran this one. So now you can do the same thing for this table. So I just skip this one. So this one is like, you know, you do it like so first you compute the divided difference over 2 points, and you find the line that connect 2 points, yeah. And then the line P1 here, you just plug in the 1.3 to see what is the interpolation values. Okay, and then you do the same, but now this time you use cubic interpolation. So you compute the divided difference table. Okay, so this one, you know, I mean, you can do it by MATLAB. Just plug in the data here, and you get out those coefficients. This is your cubic. You can see that the cubic gives you a better interpolation because the error is smaller. Yeah. But anyway, so now we finished Newton's form of interpolation. So there's another form of interpolation, but we are not going to details. Okay, it's called Hermite interpolation. And this type of interpolation, you can specify the derivative. So here, you see J is just a derivative of order J. So, you know, in some cases, like you want, you know, the curve is smooth enough, and then you have to specify the derivatives has to satisfy some constraint. And, you know, in that case, then you have this Hermite interpolation. So suppose, like, we have this example. Suppose I want a polynomial that satisfy those conditions. Yeah. So what is the degree of the polynomials? So you see, now you have the values, yeah, and you have derivatives as well. But now, what is the degree of P in this example? So first, you have to identify what is the degree, and then after that, we try to find it. So what degree of P in this case? So degree 1, 2, 3, 4, 1. Well, degree 1, then it's just a linear, a line. The line, then you have only 2 constraints to specify the line, right? Ax plus b. But now you have 3 conditions. So it cannot be a line, right? Huh? Quadratic, yeah. So quadratic, then you have 3 conditions. So here you have like a0, a1x plus a2x squared, right? And then you have p0 equals 0. So therefore you have a0 just equals 0, right? And then p1 equals 1. So you have a0 plus a1 plus a2 just equals 1. Then p prime at 1 equals 2. So what is p prime? So p prime is just a1 plus 2a2 x, yeah? So p prime 1 is just equal a1 plus 2a2 equal 2. So now you have a0 So then you have A1 plus A2 equal 1, A1 plus 2A2 equal 2. So you can find out what is A1, what is A2, right? So it has to be a quadratic. So in general, you know, I mean, first you look for the number of conditions, okay? And then from the number of conditions, then the degree of polynomials is the degree m minus 1. So in our case, we have 3 conditions. So this means that we have to look for degree 2 polynomials. Yeah? But we are not going to details, you know. So this one is just give you the ideas that, okay, sometimes you need to interpolate the derivatives as well. Okay, but we are not going to details. So what happens in Hermite interpolation when there is only one point? Then what is that? Polynomials. Something well known to you. Suppose you know the you know the value, derivative, order 1, derivative order 2, derivative of order 3, and so on. And what polynomials that give you that? Huh? No, not a constant. Suppose, you know, I mean, there's only one node, so it means that, you know, like P, say 0 equals something, right? And then, you know, P prime 0 equals something. And P double prime 0 equals something. And so on. So then, what polynomials is that? Taylor polynomials, yeah? So it's a special case. So when you have only one point and you know all the derivatives, then just a Taylor polynomial. Okay? So we will skip this one. So now we go back to the errors of the interpolation. So now, so remember that, you know, I mean, you have a collection of points, remember? So this one is x0, x1, up to, say, xn. Or maybe say x1 up to xn plus 1, yeah? Then you have y1 here, y2 here, up to yn plus 1, okay? So your interpolation polynomials, it's just a blue line like this. Sorry, a blue curve like this, yeah? But your exact function could be something like this. Well, I mean, it has to agree on the interpolation point, yeah? But at other points, then it might not be agreed, yeah? So suppose you take a point x here, then there's a error. There's a difference between the blue and the red one. Okay? And now we are interested to know how big the errors can be. Okay? You have to estimate how big the errors can be. And that is the topic of this section. So you see, you take the f of x and you minus the interpolation polynomials Pn at x. Then this is a function of x. Okay, and you denote it like the error function, En. And you can see that the errors, you know, you want it to be small, right? Otherwise, what is the point of interpolation, right? But how small it can be. So this theorem will give you, you know, the estimate. So now the error will be like this. So before I give you the theorem, let's give you a definition. So suppose that we have a function f and we call it CR if you can have all the continuous derivative up to order R. Okay? So if it's continuous, then R just equals 0. If it's continuous differentiable, then it's C1 and so on. Yeah? If it's twice differentiable, then C2. So now there's a theorem that gives you the errors. So the errors can be written as, you know, this form. Okay? So look at this one. So x is any point. in the interval from x1 to xn plus 1. Yeah? And xi is just some number in between. Yeah? So how do we prove this theorem? So, well, first we have to prove the mean value theorem for divided difference. So this is the mean value theorem for divided difference in a very general form. But now, look at the special form. Suppose, this theorem, but I just have n equal 2. Yeah? Well, actually n equal 1. Okay? Then, the theorem says that there is a point xi so that f divided difference over x1, x2 will equal f prime xi over 1. And what is this theorem? So now if you remember what is the divided difference over 2 points, so it will be just fx2 minus fx1 divided by x2 over x1 equal f prime at xi. So xi is between x1 and x2. So what is this theorem? Mean value theorem, yeah? So it's just a mean value theorem. So now, so that's why this one is just a generalized of the mean value theorem. Okay? So now, so what happens if I have like 3 points? So what happens if I have 3 points? So if I have 3 points, so n equal 2, right? Then I have fx1, x2, x3 will equal f double prime xi over 2 factorials. Okay, so that is the n equal 2, and so on. So this one, can work for n plus 1 points. Yeah, question? Where does the n factorials come from? Very good point. So now we have to prove it, in order to see it. Okay, so now suppose I try to prove this n equal 2 thing. Yeah. So now let me prove it for this special case. Okay, and then we try to see where does the 2 factorials come from, yeah? So now I say that, okay, now let me take P2, okay, is the polynomials that interpolates f over x1, x2, x3. Yeah? Okay? So then, what is P2? So P2 will be a polynomial that P2x1 will equal f of x1, P2x2 equal f of x2, and P2x3 will equal f of x3. So why I write P2? Well, because it's a polynomial of degree 2, right? Because you have 3 points. You have a parabola that goes through uniquely. You have a unique parabola that goes through 3 points, and the degree just equal 2. Okay. So the first step, and what is the next step? So the next step is, now I will write P2 in Newton form. Okay. So if you remember the Newton form, then I can write P2 like, f of x1 plus f of x1 comma x2 x minus x1, then plus f x1 x2 x3, the divided difference, yeah, x minus x1 x minus x2, right? Yeah. And now, this one is just some polynomials, some quadratics, okay? Some quadratic. and the coefficient for x squared will be this divided difference. Right? I expand it out. I just ignore the lower order. Yeah, I just expand it out, then it looks like this. Agree? Yeah? And now, let me take this g function. So the g function will be f minus p2. Okay? So then f minus p2, now if I evaluate over x1, then it will be f of x1 minus p2 x1, so it will equal 0. And so on. So you have gx2 equals 0 as well, yeah? And gx3 equals 0. Okay? So now, what does the function g look like? So the function g look like this. So you have x1 here, x2 here, and x3 here. And the function g look like this. So it could be like this. 0 at x1, 0 at x2, 0 at x3. Okay? Yeah? And now, now anyone remember the Rolle's theorem? So Rolle's theorem is just a special case of the mean value theorem. So the mean value theorem, you know, when you apply, so now maybe, so you can see it, right? So now the Rolle's theorem, where it's just a special case of mean value theorem. Well, I will say the statement and then you will see it. So now, you know, gx1 equal gx2, right? So it means that there is a psi 1, yeah? So that, well, so this one in x1, x2, yeah? So that g x1 minus gx2 over x1 minus x2 equal g prime psi, right? So this is a mean value theorem for the function g, yeah? And equals 0 because g x1 equals gx2, right? Okay? And so maybe this one is psi1, yeah? So essentially, you know, I say that similarly you can have psi2. So similarly, there's a psi2 so that g prime of psi2 equals 0. So psi2 will be in x2, x3. So you just apply in the second intervals, yeah? So far so good, yeah? So now what is my g prime? So g prime, so now I label like my g1 is g prime, okay? So what does g1 look like? So G1 look like this. So G1, so you have psi1 here and psi2 here, right? So then this is your function G1, right? Get it equals 0 at 2 points. Yeah? And now you apply Rolle's theorem again. Okay, so Rolle's theorem is just a special case of mean value theorem. So then you say that, okay, so G1 psi1 equal G1 psi2 equals 0. So there is a psi3. So psi3 will be in the middle of psi1 and psi2, right? So that psi3 prime will equal 0. Sorry, this one psi1 prime, yeah? And this one is just psi1 minus G1 psi1, G1 psi2 over psi1 minus psi2, right? Okay? And now I just look at the last, I just look at the last one. So what is G1 prime? So G1 prime is just G double prime. Okay? So now I just look at the last one. So G prime at side 3 equal 0. Yeah? So G double prime at side 3 equals 0. So G double prime at side 3 equals 0. I just pay attention to this, the last one. Okay? So I cannot do further because now you cannot apply any theorem anymore, right? Because now you have only one point. Yeah? But now look at what is the function g. So if you remember, g is just f minus p2. And now you take the derivative twice. Then this one is just f double prime. And when you take derivative of a polynomial of the quadratic, when you take the derivative twice, what do you get? Huh? Get a constant, yeah? And you get a constant. And what is the constant? So what is the constant in our case? So if you look back to the definition of P2, so this is a constant multiplied by 2 factorials. Yeah, because you take the derivative twice, so you have to multiply by 2. Yeah? So this one will be f of x1, x2, x3 times 2 factorial. Yeah? And now you just rearrange it, then you have, you know, g prime psi 3 equals 0, just equivalent to say that f double prime z3 equal f x1, x2, x3 2 factorial. So now you have the theorem. So does it answer your question where the 2 factorials come from? Yeah? So 2 factorials just come from when you take the derivative twice. And you can do the same in order to prove the general case. You just keep taking the derivative, you know, n times. Then eventually, you know, you can prove the general theorem for the general case for n, for general n. Okay, because you know the same techniques just get repeated n times. Right, until you got to the only one point, yeah? So you get the idea, right? So the idea just... And you can find the proof, the general proof in the lecture notes. So we go to the lecture notes, you will see that there's a full explanation there, but for the general case, for n, for any n. But here I just do it n equal 2. Okay, but once you understand n equal 2, then general n is just the same. Yeah? So, question? So zeta 3 comes from the mean value theorem. So here. So see? So, you know, when you have zeta 1, zeta 2 equals 0, then there's a zeta 3, so that, yeah, it's come from the mean value theorem. We just use mean value theorem again and again. Okay? So this step is from mean value theorem. Okay? So now go back to the errors. Go back to the errors theorem. So the errors theorem, you know, I mean, say that if you go back to the Newton form of the interpolation polynomials, okay, then, you know, when you introduce a new point x, then this one is just the new coefficient. Okay? So remember we have the very first one. Let's say okay, so remember we have this equation, right? Yeah? So now, if you have a new point, so we look at this equation, right? So what you have is Pn x, minus, so suppose I take f of x yeah, minus Pnx, then I just have f of x minus f of x1 minus, plus minus a1 x minus 1 and so on. Yeah? And now, suppose you add on a new point, okay? Then, so if you add on a new point, then it will be something like this. It will be a product of, like, so x minus x1, x minus, no, maybe let me rewrite it. It's a bit unclear, yeah. So maybe suppose I have Pn of x equal f of x like this, yeah? A1 x minus x1 plus up to an x minus x1 to x minus xn. Okay? So suppose I have a new point z. So suppose I have like, so this one my original interpolation point, yeah? And now I add on one point. So it will be like, say z, then will be x1, xn plus 1, then z, right? Then what is my new interpolation? So my new interpolation will be Pn plus 1 will equal f of x, so this one x1, yeah, plus a1 x minus x1 up to an x minus x1 x minus xn, and plus an plus 1, yeah, x minus x1 x minus x2 up to x minus xn plus 1, yeah, because the point z doesn't come into the polynomials. Okay, so agree, yeah? And now You know, I mean now, if you take the difference, okay? So if you take the difference between Pnx, well, Pn plus 1x, yeah, minus Pnx, then what you have is just An plus 1, x minus x1, x minus x2 up to x minus xn plus 1, yeah? Okay? Yeah, so far so good, yeah? But now, suppose I put x equals z. If I put x equals z, now I put x equals z, then what happened? So if I put x equals z, then I have, this one is Pn plus 1 equals z, yeah, minus Pn z, right? And here I have An plus 1 x minus x1, sorry, z, yeah, z minus xn plus 1. Yeah? So far so good, yeah? But now, remember, when we add 1 point z, actually, you know, this is interpolation point. So this one actually, you know, we want Pn plus 1z equal f of z. Yeah, because in the interpolation, we want the polynomials actually equal the value of the function. Okay? And so therefore, this one is just f of z minus Pnz equal An plus 1 z minus x1 z minus xn plus 1. So look at the last one. So you see it? So you agree that, yeah? So I mean, I start with Pn, right? What is this interpolation form, the Newton form? Then I add 1 point, yeah? I add 1 point, z, so that f of z equal, you know, Pn plus 1 at z. And then I just use that formula again, but for this n plus 2 interpolation points. I just take the difference, then I have this formula. So f of z minus Pn of z is just equal this product, yeah? And that's exactly what we have here. Right? So remember, z is just a dummy variable. So z is a dummy variable. So I just replace z by x, you know, at any point, right? So here you just have a z minus something, but here I just have x minus something. Okay? And this coefficient, remember, you know, it's just the divided difference over n plus 2 points. Okay, question?
Why didn't you include the z as part of, like, you didn't do x minus z at any point and simply n plus 1?
No. Remember, in the original form, you never use the last point. That is the key. You see, here, remember we have n plus 1 points, but you stop at x minus xn. Okay? So the z actually come only inside this coefficient an, right? So you see the an plus 1 here is actually this one, yeah? So instead of writing z, I just rewrite x like this. But it's just the same, you know, because it's a dummy variable. So agree that from the Newton form, then we get this equation, right? And this x can be anything, right? Okay? And now, so this one is known. You know, because you know all the point x1 up to xn plus 1. Okay? Only this term, then you use the mean value theorem for divide difference. We proved it before. Then we get out this one. And then after that, you put 10 together. So you put 10 together, then you have this theorem. Sorry, this this theorem. Okay? So you agree now? Yeah? So we prove this theorem by 2 steps. First, we use the mean value theorem, generalized mean value theorem for divided difference. And then after that, we just play around with the Newton form. You know, and then you combine the 2 results and you get this statement. So now we have one example to show that, you know, how we use this theorem. Okay, so this show how do you use this theorem. So suppose you have 1, 0, 1, 2, 3. Yeah. So sorry, 0, 1, and x3 equal 2, right? So what is n in this case? So in this case, then n. No, actually, this one x1, yeah. So x1, x2, and x3, yeah. And so then we have, you know, the errors. So the errors will be f x minus b2 of x, okay, will be equal f 3 derivatives, some psi over 3 factorials, then x minus x1, x minus x2. So this one is e of x, yeah, time x minus x3. And remember, because we assume that the third derivative, the derivative of the order 3 is always less than or equal to 3. So you say that is always less than or equal to 3 over 3 factorials, then x minus x1, x minus x2, x minus x3. And now the question says that what happens when you put x equal 1.5? Then you have e at 1.5 is bounded by 3 over 3 factorials is 6. And this one is 1.5 minus 0, 1.5 minus 1, 1.5 minus 2. So you put in the calculator, then you get out some number here. Okay? Okay, so that is how you apply the theorem. So I think we take a break for 5 minutes, yeah? So then we start again. Is it okay? Okay. Huh? Like this? Okay.
So, I'm just wondering how we're supposed to like find the epsilon for which f to be and that formula holds.
Which one? Sorry.
For theorem this. I'm wondering how we're supposed to find this epsilon.
No, the sign.
Oh, sorry.
Well, you don't know. You cannot find because it's come from the mean value theorem. The mean value theorem said that there's a point in the between.
Okay.
You know, so you cannot you cannot find it. But that's why you have to use some estimate like this. You know, I mean, if you put in xi, then xi is still between 0 and 2. Then you can use this upper estimate.
Okay.
Okay? Question, yeah?
Are we going to revision for the exam?
Yeah. Now.
Oh,
After this, yeah. I mean, we just have a few more slides left, and then we start to do the revision. Okay? Yeah.
Anything on the papers for permanent interpolation?
Permit interpolation,
Yeah,
yes.
can you show the example again? Like the paper, I was the part of solution. Like one of the slides. Permanent interpolation.
Yeah, you just, have an equation, but I didn't solve it. I didn't solve it, so you have to solve for A1 and A2.
You get y equals x squared.
Huh?
You get y equals x squared. So a0, a2 is 1, a1 is 0.
Yeah, A2 just equal 1, yes. Then A1 equals 0. That's it. Square.
How do you get this bit?
No, this one is another example. This one is the next example. This one is like another example.
When even node?
Yeah, only
Okay.
one node, yes. Suppose you have something like this. Yeah, this is another example.
Okay, I get it. Okay.
Okay? And we just, this is a title for the time. Okay?
Okay. Thank you.
Okay, yeah?
I'm just a bit confused about G.
Yeah. G equal F minus
What,
B.
what do we assume this for all the time? Where do we get this one from?
No, we just define G equal F minus
How do you know it's 0? Why is this one the same as that?
Well, because f of x1 equal p2 of x1.
How do you know that?
That's what I define p2.
Oh, okay.
I define p2 to be the interpolation polynomial over 3 points.
Wait, P2 is so like
Interpolation. Yeah, you
interpolation
choose
is like the x1 minus x minus x1, x minus x2.
exactly something, some interpolation polynomials,
Oh, okay.
by Newton form.
Oh, okay.
Yeah, okay?
Thank you.
Okay, so we just try to finish off the interpolation and then we review for the midterm, okay? So for the interpolation, we have only a few slides left, and then we start for the midterm. So now you have, an example like this. So suppose I have a function f equal 1 over 1 plus x squared, and then you construct the interpolation, using degree 4 polynomials, and you can see that. So this is my f of x, the blue curve, and the green one is the polynomial, and you can see that the error is very big. See, look at the error. So the error here is very big. And you say that, okay, I can increase the degree of polynomial. So I increase it to 15 points. Yeah. And you can see that the blue is the exact function. But the green one Yeah, the green one is the interpolation polynomials. So it's very good in the middle. Yeah, but you see that there is still very big errors at the two ends. See, errors like 1, you know. You can see that the errors now is very big. And now how do we do it? How do we fix the problem? So how do we fix the problem? Now you just keep increasing n, but then still got very big at the two end points. So how do we fix it? You see the problem? The problem is, you know, you get a very big errors at the two ends, -3 and 3. Huh? Yeah. Yeah, but you just make it complicated. Yeah, but I agree you can do that. You know, like you just chop it up into 3 parts, and then, you know, at the other 2 parts, then you do some extra. But essentially, you can do that, but it's just a bit complicated. But there's a simpler solution that you just put more points at 2 ends. Yeah, just put more points at 2 ends, and then you have a better interpolation. See, this one is you have a uniform. You know, the red points are equally divided, equally spaced. Yeah, but now if you put more points at the 2 ends, then you improve it. Okay, but you are not the first one. Okay, Chebyshev, he knows it 100 years or 200 years ago. Okay, and then, well, we will study his points. You know, so now what happened is we just try to explain the behavior. So the behavior comes from the error function, right? So remember the error function, you know, you forget the constant, then it's just like this product of x minus on the interpolation point, yeah? And when you plot it, when you plot the errors function, then you can see that it's very big at the 2 ends, yeah? So you see this one is like you have 14 points. So error is very good in the middle, but then at 2 ends up to like 10,000. Yeah. So the problem is at the 2 ends. And so Chebyshev believed that you can fix that by introduce what he called a Chebyshev points. Well, people now call Chebyshev points. He's a Russian mathematician. I think maybe in the 19th century. Okay. So what he does is he just take a circle or half of the circle, and you divide it equally on the arc, yeah. But then after that you project down to the intervals. So when you project out the intervals, then you have more points at the 2 ends compared with the middle. Okay, you can see it from the pictures, yeah. So, you know, I mean, if you have a circle here, then the arc here, when you project it down, just more points here at the 2 ends. And the formula is given like this. So this one is just a simple formula. You know, you just take cosine and then project it down. And then you can see that for Chebyshev points, then the errors function look better. See, before like 10,000, that now reduced to 1,000. And now if we use Chebyshev points, yeah, then the interpolation look like this for degree 4. And degree 14, you see, very good. Okay? So you are not the first one who saw this problem. Okay? So people saw it like 200 years ago. So you have to solve something harder. Quantum computing, you know, something like that. Teleportation, hologram projection, you know, something fancy, you know. So those problems is like 200, 300 years old already. Yeah? So anyway, so now we look at the errors, and the error is just going down the Chebyshev point to machine errors. Okay? And this is a MATLAB program how to plot it. So at n plus 1 point, and those are in Moodle. And this one is for evaluate the error function. And this is how you compute the set point from the formula. Okay? The formula is just from the fact that you just draw a semicircle and you divide it equally, the angle equally, and then you project it down. Okay? So just it's an exercise to work out the formula. So that is more or less everything about interpolation. And now we have to move to the review for the midterm. So any question about interpolation? Everything is clear? Crystal clear, yeah? Okay. Okay, so now I just open Google Documents, you know. So because many people say that they cannot come to the lectures, so they want the solution recorded. So hopefully we can work on this one. And, you know, if we haven't finished, then please go back to this one and, you know, work on the Google document, okay? So I will work on the paper and you work on this Google document, okay? So go to Moodle and check whether you can get into this. So in my case, then I just work on paper. So now I have to pull back. What is the question again? So anyone, can you get to this Google form, yeah? Sorry, Google document, right? So this one. Click on this one. And now I have to choose the, what is the problem? So the problem is, practice here. Okay, so now so somebody just type it up into the Google Documents, okay? So I just work on this paper. So question number 1. So review, yeah? So question number 1, suppose you have y equals square root 1 plus x squared minus 1 minus x squared. Okay? So x very small. So you can see that, you know, this formula could have a catastrophic cancellation. So catastrophic cancellation. So, you know, you can write a very long sentence to explain things, you know, but I just look for the keyword, okay? I'm a bit lazy, so I just look for the keyword. And the keyword here is catastrophic cancellation. You have to emphasize that is the key thing here. So two things can be close to each other, and when you subtract them, then you can have a catastrophic cancellation, okay? And now how do we fix it? So you fix it by so in this case, I just, you know, there's many ways to fix it, okay? But in this case, I just multiply and divide it by the conjugate of the square root. So you multiply and divide it by the square roots. I mean the conjugate of the square root, yeah? And then you have, on the top, you have 1 plus x squared minus 1 minus x squared over 1 plus x squared, 1 minus, sorry, this one should be 1 minus, yeah? 1 minus x squared. And you see this formula doesn't have catastrophic cancellation. Yeah? Because there's no difference between the two close numbers. So question number 2, binary representation of 193. So this one I can look at the solution for tutorial week 3. Sorry, week 2, yeah? Okay, so look at the solution there. I mean, I think I did this one already. I just look at back. So now question number 3. Huh?
Do you care how we get to the answer if we use like a different algorithm than the one you gave?
It doesn't matter, but you have to give me the correct answer because I just double check whether you give me the correct binary representation. Yeah. So either algorithm is fine. Question.
So back to the number II, the reason why that is not the cache cancellation is because of what?
Because there's no more difference between the two real numbers. Because this are a plus, yeah. So it's multiplication. So there's no more, minus of the two real numbers. Because remember, catastrophic cancellation occurs when you take two floating point numbers are close to each other. Okay, and here in this expression, there's no, difference between the two floating numbers. Okay. Okay. So question 3. So what is the relative machine precision? So you can define either way. You can define that epsilon is the smallest number. Smallest positive machine number, so that 1 plus epsilon is bigger than 1, yeah? Or you can say that epsilon is the gap between 1 and the next machine number. So if you put in epsilon is like 2.2 10 to the minus 16, then it could be incorrect. Okay, because epsilon could work for, this definition could work for any number of digits in the floating point representation. Okay, so just don't put in epsilon equal 2.2 times 10 to the minus 16 because it's only valid when you have 64 bits. Yeah, so this is a general definition. Okay. So give the results for so this one you can double check with MATLAB, yeah. So 1 plus epsilon 2 equal 1. So this one gives you true, yeah? So it gives you 1. So you just put in either 1 or true because epsilon over 2 is something smaller than epsilon. So it's considered to be 0, yeah? And then 1 plus epsilon should be bigger than 1. So this one will be false. So this one double check with MATLAB, okay? Question? No, real mean is different. So real mean is the minimum normalized real number. Okay? And the value will be something like, e to the minus 308. But epsilon is just a gap when you turn the bit, the last bit, 1 to 10 to the minus 16, 2.2 10 to the minus 16. So real mean and epsilon are different. Yeah, question? Yeah. In single precision and double precision are different. Yes, yes. Yes. Yes, yes. Because if you write actual number, then it means that you are just give a definition. You just assume double precision. Question, yeah.
Does the computer round up? So if I say 1 plus 3/4 of epsilon is greater than 1, will that work?
Well, you can check. I think so. So you said that 1 plus 3/4 of epsilon is still smaller than epsilon, right? Sorry, still
Is greater than 1.
Well, you can check MATLAB. It says that 1, so it's correct. So there's some round off, yeah.
Okay, so it rounds up.
Yeah. So round off, yes, I agree. Because now if you say that epsilon over 2, let's say no. So there's some round off, I agree, yes. Okay? So over 2 bigger than 1, say no. Yeah, but but 3/4 then let's say 1. That's a bit tricky, yeah. So any question? Any more question? Okay. So move on to the next question, yeah. So next question is well, question number 4. Just check my MATLAB. I think. So question number 4, you just have a vector and you just take the command a equals 0. So this one just so it means that it just check, you know, like what entries equal 0. So you can see that the first entry equals 0, so it's just 1 here, and then non-zero. So it will give you the answer like this. So this one just put in MATLAB and you can check. Okay, so this one just check that you can know some MATLAB, some simple MATLAB commands, yeah. And sum is like sum over the columns of the matrix, and so suppose I have B equal 201 minus 304. That's sum of B. Then you just have just sum over the columns. Okay, so it will be like minus 1 and 0 and 5. Okay. So this one just check that you understand you know some simple commands. So and then you can do the same for other questions. So we move for the number 5. Yeah.
What is sum of B?
Sum of B, then it will take the sum of all 3 elements. So sum of B. So because then it's just a sum of this vector, so it gives you 4. Okay. So sum of B, you just take the sum of the columns. Okay. So this one just then it gives you a row vectors. So you can double check with MATLAB. And NZ is just a number of non-zero. Okay, so we can just plug in MATLAB and you can check it. Okay. So this one just test that you know some simple commands in MATLAB. And number 5. So number 5 question.
So if sum B would be the sum of the columns,
Yeah.
what would be the MATLAB command for the sum of the rows?
Good question. I think you just sum then comma 2. You know the I can show you. So suppose you have B equal 2, 0, 1 minus 3, 0, 4. Yeah? And if you take sum of B, so it gives you so suppose the matrix B look like this, yeah? 2, 0, 1, yeah, minus 3, 0, 4. And you take sum of B, then it gives you the sum of the columns, yeah? But when you want to sum the rows, then you say that sum of B, comma 2. Okay? 2 for the second dimension. Okay? Then it gives you the sum of the row. Okay? And when you say sum of B, give you the whole thing. Okay, sum of 4. Yeah. Okay, question. Yeah, logical. Yes, double equals mean that whether A equal B or not. But single equals like you assign the value. Okay. So now the next question is about the relative errors. So question 5 is like you have, so I think this one I did in the lecture note already. So check in the lecture note, yeah. So this one in the lecture note, I think check the lecture notes in chapter 2 for question 5, okay? So please double check the lecture notes. I think I did this. You can do the calculation here again, but I think it just take a lot of time. And now, so this one related to your lab question in week 3, yeah, or week 2. How do you solve the quadratic equation, right? And then what is the input and the output? So the input and the output. So input will be A, B, and C, right? So A, B, and C. And output can be, like x1 and x2. And now what is the first line? So the first line is just write down function then x1, x2 equal quả solve ABC, right? So this is the first line. That's it. Yeah, so this is the first line of function quả solve. And to use the function, how to use it. So this one related to the lab in the second week, yeah. So you just write quả solve 2, 3, minus 1. So see, I don't ask you to write the full program, but I just ask you to write, the first few lines. And then, for you just A equal input something B equal input, C equal input, and then you just quả solve. So x1, x2 equal quả solve of A, B, and C. Okay, so the script just simple like this. Only a few lines, yeah. So question number 7. So So number 7, the relative errors will be the relative errors will be x minus pi, right? Sorry, will be pi minus 22/7 divided by pi. And so for this type of problem, then you need to put in your calculator, okay? And then you have some number, so just put in. So here I did some calculation and I have 0.4. Just verify the calculation, okay? So this I did some calculation before. Ten to the minus 3. Okay? So but now what I want to focus on this one is a number of significant digits. You know, so now this one is less than 0.5, 10 to the minus 3. So it means that I have 3 significant digits. Significant digits. So the definition of significant digits was given in the lecture note in section in the chapter 2. Okay? And you can do the same for, you know, another number. Yeah? And now sorry?
What's the significance of the fact that there's only 3 significant digits? Because it's finding like the percentage error.
Yeah.
So if it's like it's not.
It's
the
a
absolute error is where we consider like the.
Well, I know what you mean, but see, this one is just like the definition from IEEE. And you know, when they say the relative errors is less than, you know, 0.5, 10 to the minus p, then, you know, it means that can be p significant digits. You can say that in the relative errors terms, you know, but then this one in terms of the digits.
Okay, so we just got the definition of standard.
IEEE, yeah. So there's somewhere there's, you know, like IEEE, they just define like this, and we just use it. Okay. So now the next one is back to MATLAB again, yeah. And for the number of significant digits, you know, if you look up on the internet, there's many definitions. So for this class, we just stick to one definition here. Okay? So if the relative errors is just less than 0.5 times 10 to the minus p, then we say that it has p significant digits. Okay? Okay, so question 8 is you have a MATLAB. Well, you have a formula, and now you want to write an anonymous function. So the p-val will be s and t, then s to the power 3 times exponent of minus rs. Okay, so this is how you define the anonymous function. because the function here is given with a formula, and you convert into anonymous function, and it depends on 2 variables, s and r. Right, yes. So this one should be s and r, sorry, not t. Yeah? So S and R, yeah? And then you can define as a MATLAB function. So you can define as a MATLAB function as well. So if you define MATLAB function, then you write function P. So you can choose either one, right? Either this or so the function P equal P val S and T. And you give the formula again. So now, question?
Sorry, why don't you have a dot next to the multiplication between S cubed and the exponential?
Good point. So should be a dot here, yeah?
There should be.
Should be a dot everywhere because it could be a vector, yeah? Okay? Yeah?
It's okay if it's not a vector, right?
It's okay, but not a vector, yes. But you know, I mean, you just put in a dot, then just in case of the vector, then it will evaluate for you, yeah? Question? Yeah? For one, if you have one output, then you don't have to have a square bracket. You can have a square bracket, but you know, you don't have to if you have one output. If you have more than one output, then you have to put in the square brackets, then comma, you know, like Quasov, you have open bracket x1, comma, then x2, then close bracket. Okay? And then for the next one, then how do you use the the p-val in the double integral? So then, you know, I mean, you can say answer equal double integral 0, 1, 0, 1. Oh, sorry. Double integral, yeah. So you have to put in the p-val here, 0, 1, 0, 1. So if p-val is anonymous, yeah. So if p-val is anonymous, anonymous function, but if it's not anonymous function, if it's defined in the MATLAB files, then you have to put in a function handle. So the function handle here, if it's if it's defined in the file, pval.m. Yeah. So if it's anonymous, then you don't have to put in this function handle, right? But if it's not, if it's defined in the pval.m, you have to put in a function handle. Okay. Question?
Do you also need to put the R and S values into people?
No. So that is, you have to check with MATLAB, but that is the case. You don't have to put in any input here. You put in the function name only.
So how do they know where to evaluate R and S?
Well, it passed in the function handle and it passed in the range. You can play and check. It will work, yeah. Okay. And now LU factorization. So this one for number 9. So please check tutorial solution yesterday. So check, or maybe today, yeah. So check solution of tutorial week 3, yeah. No, sorry, week 4, yeah. for question number 9. Okay. So this is exactly the problem from the tutorial for week 4. Yeah. So it's lengthy, but I'm not going to repeat it. And now for question number 10, solve the 4x4. So this one, they give you the LU factorization, okay? Then how do you use it to find A inverse? So you see, you explain, you don't have to solve it. Okay, so for the second one, you don't have to solve it, okay? Only for the first one, you have to solve it. Then you see it very quick because the LU factorization has been here already. So now for number 10, so you solve, like LU x equal b. Then you solve it in 2 steps. So step 1, you solve Ly equal b. So y is here, then ux equal y. Yeah. And you can see that you have the matrix L already. Yeah. So the L will be so you solve Ly equal b. Then you have the matrix L, so L is given, so 1 minus a half, 1, 1, 0, 1, 1 quarter, 0, 1, 1, and y1, y2, y3, y4 equal b. Yeah, so b is 4, 5, 16, 16. Right? So you can get y1 equal 4. Right? And y2 is just equal 1/2 of y1, right? It's equal 2. And then y3 equal minus, well, actually it's not 1/2, should be 5 plus 1/2. So it goes 7, yeah, because we have to take the 5 here, yeah. And then y3 it's just 16 minus y1, so just 12. And y4 it's just 16 minus 1 quarter y1 minus y3, yeah, from the linear system. So you have 16 minus 4 minus 12, just equal 0, okay? So you can solve it, and then after that, when you have a vector y, then you solve ux equal y, yeah, and you have the matrix U here. So it's not hard, right? Just put in some calculation.
So y4, 1 quarter y1, I think.
1 quarter y1, yeah?
Yeah, so that should be 1.
Should be 1, okay, sorry. So 15 minus, so it should be 3, yeah? Okay. So, and maybe just do the other one. So just, it's not hard. And explain how you use LU factorization to find A inverse. So I just leave the detail for you to fill up, yeah? So you can explain that you can find AX equal identity by LU X equal identity to compute A inverse, yeah? So then you solve L, say maybe W equal identity, then UX equal W. and then. Okay? So that is how you find A inverse by AU factorization. So we are not going to solve it. Okay, so question number 11. So 11 is, what is the Cholesky factorization? So Cholesky factorization is just R transpose R, and you say that R is upper triangular matrix and with non-zero diagonal entries. Okay, so that is the Cholesky factorization. So what are the necessary sufficient conditions for A such that this factorization exists? Well, asymmetric and positive definite. Okay. Yeah. Okay, so question 11. Sorry, 11 is done, yeah? So question 12. 12, what is the condition number? So the condition number is A times A inverse, yeah, in the norm. So any norm. So this one is when A is non-singular and it equals infinity when A is singular. Okay. And now prove that So prove that condition number of AB less than or equal condition number of A times the condition number of B. Okay. So this one in the lecture notes, and you have to prove in 2 steps. So first, you have to prove A times B, take the norm is less than the norm A times the norm of B. Right? So how do we prove it? So remember just the definition. AB norm is just max of AB V over V. V is non-zero, right? And then this one will less than or equal the norm of A times max BV over V. And this one is just the norm of A times the norm of B. Yeah? And after that you just take the condition number of the product. Okay, so then it just equals the norm of AB times the norm of AB inverse. And you use the results there, just less than equal the norm of A times the norm of B times the norm of B inverse times the norm of A inverse. And this one gives you the condition number of B. And this one give you the condition number of A. So you prove it in 2 steps. First, you have to prove the norm for the matrices, the product of the matrices, and then after that, you use the definition of the condition number. Okay. So this one has been done in, I think, in the lecture notes or in the question.
Why can you pull out the A norm there?
Yeah. Sorry, I skipped 1 step. I did a bit more in the lectures. Okay, so let me elaborate a bit more, yeah? Okay, so now Good point. Yeah. So how can I pull out A like this? So go back here. Okay. So go back to this one. So go back to this one a little bit. So now remember that the norm of A is given by max of AW over W norm, right? W is non-zero, yeah? Okay? And because it's maximum over all the vectors, so in particular, if I choose the W to be BV, then it's bigger than ABV. Okay, agree? Yeah? And this one is still write a norm like this. And now if I cross multiply, then I have a norm times the norm of BV is greater or equal ABV. The norm. Okay. So you got it? So it comes from the definition. So the star, so actually the star here, this one. It's a bit too fast, yeah, but it comes from that, yeah. And then you can pull out the norm of A. Okay. So any question? So now the third one say that, okay, so what happens if the condition number is 10 to the 10? So if the condition number is 10 to the 10, and then the exact values of A and B are given, then what can you get from the accuracy for Ix equal B? So you have to say that the relative errors in X will be less than or equal the condition number of A multiply the relative errors in B, in vector in the matrix times the relative errors in the vector B. And in this case, because they're known exactly, so it means that you just have epsilon for each of them. And this one is 10 to the 10, and this one is about 2.2 times 10 to the minus 16, 2.2 10 to the minus 16. Okay, then you get some number. Okay. So then we may not have time for the last three questions. But so let me post the solution for the last three questions, okay, in the Moodle page. I mean, sorry, in the Google documents. But you can see that, I mean, say number 16 was done in the tutorials, yeah? So number 16 was done in the tutorial. So only 17 and 15, something that related to this inequalities, okay? But,